Oh, hi. I didn't see you there. I was just thinking about multi-criteria decision analysis on a Saturday afternoon. It's good stuff. In the last video, we talked about ways that we can try and identify a preferred project without explicitly having to consider trade-offs between multiple impacts. In practice, we might use dominance to eliminate a number of projects from consideration that would never be picked regardless of our relative preferences for different impacts. The other approach is satisficing, in which we set a minimum threshold of performance for a given criteria, and as long as the strategy is on the acceptable side of that threshold, then we can evaluate it using other criteria instead. Sometimes we still have multiple projects in contention after applying these non-compensatory methods. So then what do? We need some way to evaluate trade-offs, because otherwise we need to ask decision makers to make sense of a plot like this. In this case, we have a three-dimensional plot where the x, y, and z axis all represent one particular criterion. We have these cones that have a particular size, indicating a fourth metric, an orientation, whether it's turned up or down or to the side, representing a fifth metric, and then we have the color, which also specifies a sixth value. So here we have something that is really complicated, and decision makers, if you give them this plot, they're going to kick you out of the room. Or here we might have what's called a spaghetti plot, where each column represents the range of outcome values for a particular criterion, and the string that's connecting one point to another, going from column to column, represents a single potential solution or strategy or project. Clearly this is pretty complicated, but it's not that uncommon to have a system where you've got 5 or 6 or more different indicators summarizing the system performance. So when we are trying to design a system on the basis of all those different things, we can present the information visually, but it's really hard cognitively to interpret that visualization and lead ourselves to a good, smart solution, choosing one option over another, when this is the type of thing that we're looking at as a decision support aid. So ideally, we want some way to reduce the dimensionality of the problem, even after we may have already done that somewhat with satisficing or dominance. The most common way that we do this is to use something called an index function. We've already seen something that we called an index earlier in the semester when we were talking about inflation, and that was boiling down the price of lots of different types of goods into a single scalar value that indicates, on average, relatively speaking, how much more expensive is something today than it was 5 years ago. We have a similar concept here, where we're just going to try and convert the set of objectives that we have into some smaller number of variables. Preferably, we want to reduce it down to a single scalar value. The easiest way to do this is through what's called a weighted linear sum, which is exactly what it sounds like. If we have a number of different criteria, then we can come up with a function for each of them, and then we're going to combine them together by taking their sum with a weight attached to each one that represents how much we care about one criterion versus another. So we can see our index function here is g. It's a function of all of the metric functions f for a given solution x. For this example, we're assuming that all of our performance functions f are something that we want to maximize, so that a higher score is better. And so that's why we are specifying that all of our omega weights attached to each of the performance metrics is positive. So that way, when we're adding them up, a larger weighted linear sum is better. If we're in a situation where we want to minimize certain impacts and maximize others, then what we need to do is flip the sign of one of them. So we might take an impact that we want to minimize, and for its performance metric f, we're going to multiply it by -1. So that way, if we're trying to minimize the value of f, we want to maximize the value of -f. Because for certain metrics, the domain and range might be on very different orders of magnitude, we need a way to account for that as well, so that the value of whichever metric has the largest order of magnitude doesn't just completely dominate the value of this weighted linear sum. So we might need to normalize or rescale the value of our outcome metrics such that our performance functions f are not just the value associated with each of those criterion. It needs to be a rescaled value. We also haven't said much about how to assign the weights, omega, to each of our criterion. First, let's talk about manipulating our data for the metrics, and then we'll deal with the weights. We want to normalize all of the metrics information to put it on an apples-to-apples scale. So what we're going to construct for each of our criterion is a value that ranges from 0 to 1, such that 1 is always the best and 0 is always the worst. We're going to be adding up all of these values ultimately into our weighted linear sum, and our decision rule that we want to use is to pick the project with the largest value of that weighted linear sum. Therefore, for each one of our individual criterion, that's why we're going to try and rescale things or flip the directionality of the data so that 1 is always best and 0 is worst, regardless of whether or not we want to minimize or maximize a particular impact. If we think about the car example, we want to minimize the price of the car. All else equal, we'd rather have a cheap car. So we're going to look at the price p sub x for a car x, and we're going to construct our metric function for price, f of x, as being equal to the difference between the maximum price of a car among all of the cars that we're considering and the price of car x. And then we're going to divide by the difference between the maximum price and the minimum price among all cars we're considering. This way, if we're looking at car X and it has the minimum price among all the cars we're considering, then the function f of x would just equal 1, because the numerator would become p max minus p min, and then we divide by that as well to get 1. If a car has the maximum price among all the cars that we're considering, then our numerator becomes p max minus p max, and so f of x equals 0, and that's going to be our worst option. If we want to maximize a particular criteria, then what we want to do is construct a function that just changes around the numerator. Otherwise, it's going to be the same as before. So we would have zx minus z min, where that's the minimum value for criteria z among all of the cars we're considering. This way, because we want to maximize z, if we have the car x with z max, f of x is going to equal 1. And if we have the worst car with respect to criterion z, then we would have z min minus z min, and f of x would equal 0. So by construction, we're ensuring that the value of f for any criterion is going to be between 0 and 1, but even more, it's going to cover the range of 0 and 1. Now that the functions associated with each metric span the range from 0 to 1, when we put a weight on them, that tells us how much we care about each criteria relative to the others. So if you would say something like, I care about price as much as mileage and comfort combined, then that means that the weight that we attach to the price function should equal the sum of the other two. Then if you care about comfort 50% more than about gas mileage, then we could use that information, translate it to a system of equations that allows us to solve for what the appropriate weights are that are consistent with those preferences. What we typically do is say that all of the weights have to add up to 1. That gives us another equation that we need in order to solve for each of them. So we would look at our first statement that says, I care about price as much as mileage and comfort combined. And that tells us omega price equals omega miles per gallon plus omega comfort. Then we have a statement that says we care about comfort 50% more than gas mileage. So from that, we can get an equation that says omega comfort equals 1.5 times omega miles per gallon. And then we apply that third equation that says omega price plus omega miles per gallon plus omega comfort equals 1. That gives us three equations with three unknowns, so we can solve for this particular set of weights. There's a lot of research out there about how to most appropriately elicit weights from decision makers or determine how to use them. For this class, we're going to stick with these simple types of statements that we're going to take on face value and use to develop equations to solve for what the weights would be. But in practice, be aware that this is pretty complicated stuff. In the next video, we'll apply all of this information to an actual example of how to select a car based on a range of different options for the price, comfort, miles per gallon, and safety.